Guys, how's it going? This is Mike coming back at you with another video on Foundations of Math 2. In the previous video, we got a little bit of an introduction to sets. What is the definition of a set? And just some basic related terminology and properties of sets. We talked about the different ways we can represent sets as well. In this video, we are going to continue discussing sets, but we're going to talk about some common yet important relationships that we can have between two given sets. But first, we need to put these special relationships and these sets in some context. You can have two sets, A and B, and these guys are typically subsets of some universal set, some massively large set, which we call U. And U is the set of all objects reasonable to consider in a given situation. Very, very common in the world of mathematics. The universal set is the set of all real numbers. Later on in the course, we'll get into more detail as to what that is. But all the whole numbers that we commonly work with, those are just some real numbers. So we typically work in the universal set of being a set of real numbers. If you want a non-mathematical sample here, if we were talking about a set A, which is the set of all Chevrolets, and B is the set of all red cars, then the universal set could just be the set of all cars. And we'll see how those tie in, how the universal set and the two sets all tie in to each other as we continue on in this video. So given a set A, the complement of A, and in the textbook it is denoted A prime. The other way that you can see this symbolized is A and then with a C in the upper right-hand corner. It's the set of all elements in the universal set that are not in our set capital A. In set builder notation, how we would state this is that A prime or A complement is the set of all X such that X is in the universal set U and X is not in our set A. Here's a real life sample. For example, if U is the set of all whole numbers 1 through 9, and A is the set containing 1, 4, 5, 6, and 9, then what is A complement or A prime? So we need to find all the guys that are in this set here that are not in this set here. So let's just go one by one and see which numbers hold to that. 1 is in U, but it's also in A, so it can't be in A complement. 2 is in U, 2 is not in A. That means that 2 is going to be an element of A complement, is going to be a member of that guy. Same goes with 3. 3 is in U, and it's not in A. And we can continue on with 4 through 9. 4, 5, and 6 are all in U and in A, so that's no good. 7 and 8 are in U and not in A, so those two are going to be elements of the complement. And 9 is in U and 9 is in A, so that's not an element of the complement. Therefore, A complement is just the numbers, or the set containing the numbers 2, 3, 7, and 8. Sometimes an object having one property means that it automatically has some other kind of property to it. In the world of mathematics, we say then that something or some set is a subset of some other set. So given two sets A and B, we say that A is a subset of B, and we denote it with this odd stretched out looking C, and then with a horizontal line directly underneath it. And we say that A is a subset of B if every element of A is also an element of B. As a non-mathematical sample here, if I talked about the set of all doctors and I talked about the set of all surgeons, every surgeon is a doctor just by nature. So we say that the set of all surgeons is a subset of the set of all doctors. And there we go. There's the sample that you just saw right there. Pulled that off of the top of my mind. It just so happens to be the same one there. Now, I do want to make a note about this symbol that we use here. That horizontal line underneath the funky looking stretched out C means that the sets could be equal. Sometimes we want to talk strictly about a proper subset. You know, something where the two cannot be the same set. So when we say that A is a subset of B and the sets are not equal, we say that A is a proper subset of B. And the symbol is the same, except we take out that little horizontal line on the bottom. And we just have A, that stretched out C, and then the set B. Here is an example of a proper subset. A is 1, 3, 7, and 9. B is 1, 3, 5, 7, 9, and 11. Every element that's in A here is in B, but there are also elements of B that are not in A. So this is why A is a proper subset of B. Every guy that's in here is in here, but there are guys in here that are not in here. These two sets, A and B, are not, A is not a proper subset of B because the sets are actually equal. A is 1, 3, 7, 9, 11, and 5, and B is 1, 3, 5, 7, 9, and 11. Again, to be a proper subset, every element of A has to be an element of B, and there have to be elements of B that are not in the set A. Yes, every element in A is an element of B, but the same elements are in the two sets. So the sets are equal, so it's not a proper subset here. It is important to distinguish between an element and a subset, as well as the notation that is used. People do tend to get tripped up on this. It can be a little bit tricky, so we're going to provide some clarity here as far as what symbol do you use when. If we want to say that a particular object is an element of a set capital A, then we write the object, typically without braces on it, followed by that funky looking E, the epsilon symbol, and then the set name. Now I'm going to underline that word typically, because 99% of the time, when you say that something is an element of a set, you're not going to be putting the set brackets or the squiggly brackets on that element. There is one particular case, though, where when you want to say something is an element of a particular kind of set, the element does indeed have the squiggly brackets on it. That is something I will show you. We're not going to spend a lot of time on it, but I just want to stress that typically when you say something is an element of a set, the thing that is an element is not going to have the squiggly brackets on it. So here is what I am talking about. take a basic set, A, 1, 2, 3, 4, 5. If I want to say that 3 is an element of the set, I'm just going to write just the number 3 and then that epsilon or is an element of symbol and then my set A. I'm not putting that 3 inside of braces. I'm not putting that 3 inside of squiggly brackets. This is not correct. This would be saying, if we wanted to make this correct, we would have to change this to the subset symbol, and then we'd be saying the set containing 3 is a subset of this set A. So if you're just talking about a particular element, typically you're just taking the number or the object or whatever and then using the element symbol and then you're writing your set. You're not putting squiggly brackets on that particular object. If we want to say that a particular object or group of objects is a subset of a set A, then we write the object or objects separated by commas and with braces on them, or squiggly brackets, followed by the subset symbol and then the set name. So, same set, 1, 2, 3, 4, 5. If I take 3, 1, and 4, and I want to say that those 3 elements make a subset of my set A, I'm taking those 3 elements, separating those with commas, putting those inside of set brackets, and then I'm writing my subset symbol, and then 1, 2, 3, 4, 5. That would be correct notation, but putting the element symbol in place of the subset symbol would not be correct in this case. So if you want to say something is an element of a set, again, not using squiggly brackets, using the element symbol. If you want to say an object or a group of objects is a subset of something, you're using squiggly brackets and you're using the subset symbol. Given two sets A and B, the union of A and B, which is denoted by A, and then almost like a capital U, and then B, is the set that contains elements that are in either A or in B. It can be in both, but as long as it's in one of the two sets, then it lies in the union of the two sets. In set builder notation, it is the set of all X, such that X is in A or X is in B. And here's just a basic sample here. Here are my two sets, A, 0, 1, 3, 4, and 5, and B, the set containing 1, 2, 4, 6, and 7. So what are all the elements that are in either A or B? We're going to take all those guys and we're going to write those as one set. So 0 lies in A, so it's going to be in, or 0 is in A, so 0 is going to be in the union. 1 is in A. 3 is going to be in A, so it's going to be in the union as well. And same goes with 4 and 5. Now, when we look at set B, if there are elements of B that were in A, we don't rewrite them. We don't write the same element more than once inside of a set. We only have to write it once. So 1 is in B. That's already in our union. So that's fine. 2 was not an element of A, so we have to include that in our union as well. 4 was in A, so it's already in there. 6 was not in A, so we include that in our union. And then 7 was not in A, so we include that in our union as well. So A union B in this case is 0, 1, 2, 3, 4, 5, 6, and 7. And again, the order in which we write these elements does not matter. Just it's fairly common that we like to write numbers in ascending order, So that's how I chose to write them. Different from the union is the intersection. Given two sets A and B, the intersection of A and B, denoted A, and then an upside down capital U, that's referred to as a cap. So A cap B. This is the set that contains elements that are in A and in B. So in order for a set to be in the intersection of A and B, that element has to be in A and in B simultaneously. This is what the set looks like in set builder notation. Set of all x such that x is in A and x is in B. For example, going with the same two sets of A and B, what is the intersection? All right, 0 lies in A, but it's not in B, so not in the intersection. 1 lies in A and it lies in B, so 1 is going to be an element of the intersection of those two things. 3 is in A, not in B. 4 is in A and it is in B, and that's going to be the other elements in my intersection. You can check 6, not in there, 7, not in there, 5, not in there, and 3, not in there. So this is what we mean by the intersection. The element has to be in each set separately in order for it to qualify to be in the intersection. Another set that we can create given two sets A and B is the difference. The difference of A and B, which is denoted A minus B, it is the set that contains elements that are in A and are not in B. So in set builder notation, the set of all x such that x is in A and x is not in B. Again, sticking with the same two sets that we used, what are all the elements in this set here that are not in this set here? So A, 0 is in A. Is 0 in B? No, it's not. So this element, 0, is going to lie in the difference A minus B. 1 is in A, but 1 is also in B. Therefore, it cannot lie in the difference. 3 lies in A. 3 is not in B, so it lies in the difference, A minus B. 4 lies in A. It also lies in B, therefore not in the difference. And then 5 lies in A. 5 does not lie in B, therefore 5 is in the difference. So the difference, A minus B, is the set containing 0, 3, and 5. So if A is the set of all even numbers, 2, 4, 6, 8, so on and so forth, and B is the set of all odd numbers, 1, 3, 5, 7, 9, 11, and so up and so forth, what are A union B, A intersect, or A cap B, and the set difference A minus B. I'm going to challenge you guys on this one. Try this guy on your own. Try to figure these guys out all by yourself. Go back to the previous slides. Again, look at the definitions of the union and the intersection and the set difference. You will need to think back to the previous video about a special kind of set that we talked about. So press pause here, see if you can come up with the correct answers. Once you think you have the answers, press play, and we'll see if you're correct. All right, so let's see if you were correct in your answers. First up, the union. A is all even numbers, 2, 4, 6, 8, 10, so on and so forth. B is all odd numbers, 1, 3, 5, 7, 9, 11, so on and so forth. So if I take the union, I'm going to get 1, 2, 3, 4, 5, 6, alternating between numbers in those sets, and all whole numbers greater than or equal to 1 is the set of all natural numbers, or n, a set we talked about in our previous video. So that's what the union looks like. The intersection, there are no numbers that are both even and odd. You probably saw that after doing a little bit of messing with it. So the intersection is the null set or the empty set. And the set difference A minus B, what are all the elements in A that are not in B? Well, A is the set of all even numbers. There is no even number that is simultaneously odd. So A minus B is actually just the set A. It's just the set of all even numbers. And this is a special yet common enough case where we have a special term for sets A and B that have this kind of deal going on. What happens, or what do we call two sets that don't have any elements in common? We say that these sets are disjoint. They're completely separate from each other in terms of the elements that they have inside of them. If two sets don't have any elements in common, then they are said to be disjoint. So that concludes our video on this common yet special relationships that we can have between two sets. The union, the intersection, the set difference, the complement of a set. Very, very important basic types of sets that you will want to know how to find. In the next video, we're going to continue talking about sets, but we're going to look at these things more visually. And we're going to do that with things that you have probably been exposed to before, Venn diagrams. If you have any questions or comments, please be sure to reach out to me, send me an email, send me a postcard, throw out the bat signal. Telegraphs work too. Until the next video, take it easy, guys.